Welcome to The Explainer. Today, we're pulling back the curtain on one of the coolest, most creative ideas in AI, Generative Adversarial Networks, or GANs. We're going to dive in and decode the beautiful math that makes them tick.
You know, it all kicks off with this really fascinating question, one that almost sounds more like philosophy than computer science. How can you actually teach a machine to be creative, to make something that feels totally new?
And the answer, which came from a groundbreaking paper back in 2014, is just so surprisingly elegant. You don't teach it to create directly. Nope. Instead, you teach it to play a game, a really elaborate, high-stakes competition between an art forger and an art critic.
All right, so let's get into it. Here's what we're going to cover. First, we'll talk about this AI forgery game. Then we'll meet the two players, the adversaries. After that, we'll see how they keep score using some pretty clever math. Then we'll break down the playbook for the critic and the master plan for the forger. And finally, we'll see how it all comes together in something called the Minimax Showdown.
All right, first up, the AI forgery game. So let's really set the stage here, because this is the concept that has just completely changed the game in deep learning, letting AI create these mind-blowingly realistic images, music, you name it.
So, at its absolute heart, a GAN is all about competition. Think of it like a zero-sum game. You've got two AI models, two neural networks just pitted against each other. And I mean literally, one success is the other's failure. They're locked in this constant digital duel.
Okay, so let's properly meet our two adversaries here. We've got the generator and the discriminator, or to make it easier, let's just call them the forger and the critic. Each one has a very specific and totally opposite job.
Okay, so this diagram really lays out the whole flow. It all starts with what we call a random noise vector. And seriously, it's just a bunch of random numbers. Think of it like a blank canvas or a block of marble. We call it Z. Now this Z gets fed into our forger, the generator. And the generator's whole job is to take that random noise and sculpt it into something that looks like a real image. We'll call that G of Z. Then, that fake image, along with a bunch of real images from our dataset, we'll call those X, gets shown to our critic, the discriminator, and its only job? Tell the fakes from the real ones.
So this is the really critical part, right? Their goals are completely at odds. The generator, it's trying to become the ultimate forger. It keeps learning, keeps adjusting, trying to make its fakes so good you just can't tell the difference. But the discriminator, it's on the other side, trying to become the world's best art critic. It's learning to spot every tiny mistake, every little flaw. And the beautiful thought is, they force each other to get better. They're literally learning from each other's failures.
But, you know, for any game, you've got to have a way to keep score. So how do these AIs know if they're doing a good job or a bad job? Well, that's where the math comes in. And it's all about measuring how right or wrong you are. Okay, so the scoreboard is what we call a loss function. Now, don't let the name Binary Cross-Entropy scare you. The idea is actually super simple. Just think of loss as a penalty. If you get something right, your loss is 0, no penalty. But the more wrong you are, the higher that penalty score goes. So pretty straightforward, right? The goal for each player is to get their own penalty score as low as possible. Okay, let's break down the critic's playbook first. How does the discriminator figure out its penalty score? Well, it has to be ready for two different situations, seeing a real image and seeing a fake one. So scenario 1, it sees a real image, X. Its job is to scream real. It does this by outputting a number as close to 1 as possible. Think of 1 as 100% sure this is the real deal. Now the formula for its penalty is negative log of d of x. And the cool thing about the log function here is that if d of x is 1, a perfect guess, then negative log 1 is 0, no penalty. But if it messes up and says, I don't know, 0.2, that penalty score shoots way up. Let's make this concrete. Imagine the discriminator sees a real photo of a cat. It's pretty sure, so it says, I'm 90% confident this is real. So dx is 0.9. Its penalty is minus log of 0.9, which is a super small number, like 0.1. That's a tiny penalty. It did a great job. Okay, now for scenario 2. It sees a fake image, G of Z. Now its goal is the total opposite. It needs to output a number as close to 0 as possible. 0 means 100% positive this is a fake. The penalty formula looks a little different. It's negative log of 1 minus d of g of z. So think about it. If it does its job and d of g of z is almost 0, then 1 minus d of g of z is almost 1, and the log of 1 is 0. Again, no penalty. So, back to our cat example. The generator makes a fake cat. The discriminator looks at it and goes, I'm only 10% sure this is real. That means it's 90% sure it's fake, right? So d of g of z is 0.1. The penalty is minus log of 1 minus 0.1, which is minus log of 0.9. And just like before, that's a teeny tiny penalty. Perfect. It spotted the fake.
And that's pretty much the whole strategy. To get its final score, the discriminator just adds up the penalty from the real images and the penalty from the fake images. And its entire mission in life during its turn is to tweak its own brain to get that total penalty score as low as it can possibly go.
Okay, so that's the critic. Now for the forger's master plan. The generator's goal? The complete opposite. It's all about making the discriminator's life miserable.
See, the generator couldn't care less about real images. That's not its problem. It wins when the discriminator messes up on its fakes. That's its only goal. Make a fake image so convincing that the discriminator is totally fooled and outputs a 1, basically shouting, "This is real."
And this is the most brilliant part of the whole setup. How does the generator figure out its own penalty? It literally steals part of the discriminator's own formula. Remember that second part, for the fake images? The discriminator wants to make d of g of z small, while the generator wants to make d of g of z large. So the generator's goal is to minimize a formula that gets smaller as d of g of z gets bigger. It's perfectly adversarial. It takes the critic's own rulebook and uses it against it. So cool. Which brings us to the grand finale, the Minimax showdown. This is where both of these opposing goals get slammed together into one really elegant equation.
And there it is, the whole shebang. PACE is the complete loss function for a GAN, straight out of that original 2014 paper. I know it looks a little scary, but trust me, we've actually already gone through every single part of this.
So if you just look at the equation, you can see those two parts we talked about. But the key is that min g max d part out front. That tells you everything. It's a two-player game. The discriminator, d, is trying to maximize the outcome of this equation. It's trying to get the highest score. Then the generator, g, takes its turn, and it tries to minimize the exact same thing. It's a constant push and pull, a tug of war, captured perfectly in the math.
Now, as elegant as this is, it's not always easy. In the real world, GANs can be a real headache to train. Sometimes the game gets stuck. Maybe one player gets way too good too fast, or the generator finds one easy trick that works and just does that over and over again. That's called mode collapse. These are big challenges that researchers are still working on solving.
So this leaves us with a pretty deep thought, right? We've seen how this crazy mathematical game of cat and mouse can actually teach a machine how to be creative. But think about it. When the forger, that's learning what reality looks like, and the critic, that's defining what reality looks like, are both just code. Well, it makes you ask, in this digital duel, what does real even mean anymore?